Welcome to lecture number 4 on NPTEL online certification course. Let me start from where we left in the previous turn and then we can go ahead discussing other parts. We will look into now the work function difference. So, we have understood the basics of Fermi level. The takeaway was when the Fermi level is close to the conduction band n type, close to the valence band p type. If you give a positive bias on the semiconductor on the metal side, the bands will go down on the semiconductor side. If you give a negative bias, it will go up if it is a n type and p type semiconductor. And as the Fermi level becomes closer to the conduction band near the surface, electrons gets added there, and as you move away from there, you have depletion region being formed there. This we have take away from a previous slide. Let us look at a metal semiconductor contact here, and let us look at the energy band diagram of a MS with oxide layer of course in the middle of it. So, we are now going in a transverse direction from metal towards a semiconductor. And now, if you look at the right hand side here, this one right hand side, then we define two important terms here. One is known as the electron affinity. Chi is defined as the electron affinity and is defined as the amount of sort of potential which you need to give for an electron to move from the lowest edge of the conduction band to the vacuum level. What is a vacuum level? Vacuum level is the one where the energy is approximately equals to 0. So, what happens is that it is not in the bound state now, it is almost like a free state, right, and the amount of potential in order to shift an electron from the edge of the conduction band to the vacuum level is referred to as an electron affinity, and the amount of energy required is Q times chi or E times chi here, right. Now, if you look at the left hand side, which is this one, then we define a term phi m here, and this phi m is my metal work function, and this actually goes from the in energy domain from Fermi level to the vacuum level, right. So, in the metal obviously the Fermi level is very close to the conduction band or almost has crossed inside the conduction band, and if you give a bias there or if you give a or the distance between in energy terms, the distance between the Fermi level and the vacuum is basically the metal work function. Now, on the right hand side again, if you look on the look at the metal semiconductor contact, and let us concentrate here. I am telling you that this EFS is my Fermi potential very close to EV, primarily meaning this is a p type semiconductor or p type silicon available with me. This is the conduction band for the p type semiconductor, this is the valence band. Now, in silicon dioxide, which is the MOS capacitor, let us assume that my band gap is very high, it is approximately 9 electron volt, and so this is my band gap and this is the conduction band of silicon dioxide and this is the valence band of silicon dioxide, and chi I is the electron affinity for oxide layer, right. So, in the oxide layer, if you want to take an electron from the edge of your conduction band to the vacuum level, we define that as chi I or intrinsic Fermi level, right. So, we have learned 3 or 4 important points. Chi is basically the one which goes from the conduction band edge of the semiconductor to the vacuum level. Phi of m is basically the work function which basically implies the amount of energy required to move from the Fermi level edge to the vacuum level in the metal. Once you have understood these 3 important terms, we try to bring the metal, oxide and semiconductor closer to each other, right. And so, I have a p type semiconductor this side, I have an oxide layer, I have a metal. Once I bring them closer, obviously what happens is that the bending on the p side semiconductor happens towards the below, because you have, let us apply a positive bias on the p side, it goes to below. Now, my EFI, right, EFI actually crosses my EF. So, intrinsic Fermi level crosses my Fermi level by application of a bias. This can only happen when your oxide conduction band shows an edge, right. So, otherwise if no bias would have been present, it would be something like this, right. With bias this becomes like this, because all the energy levels will be pushed downwards and that is what is happening here, right. So, we have now energy band diagram shown on the right hand side, and you can see here that your your intrinsic Fermi level has actually gone below your Fermi level here, and the effective value of your electron affinity has actually reduced from E chi to E chi prime, right. Why E chi prime? Because now in order for electron to move towards the metal side, the amount of energy required to pull over will be exactly equals to E chi prime, which is the oxide layer's conduction band's highest edge. If you are able to cross that, then it is a downward hill, and that is the reason your E chi I is the effective electron affinity energy at this particular point. This is energy band diagram for MOS in thermal equilibrium, right, and at thermal equilibrium I am maintaining all of the graphs here. This gives you a brief idea about this thing. I will request you to do a MOS with N type substrate on the on towards the semiconductor and apply the same principle there. Okay. Now what we do, we enter into a new domain or new area. Since we have understood the energy band diagram, we will take, because now we enter slightly into the concepts of MOS structure, right. We will take a MOS structure and try to explain to you the 3 conditions of a MOS structure, that is flat band, accumulation, depletion and inversion. And then we will finally look into the 3 terminal MOS structure and look into the defects in the MOS capacitor. This will be the outline for the subsequent few lectures or few portions of the lectures in subsequently. Now let us look at one by one. We have already done it, but this will be now a new thing which I will add here now. So look at the right hand side, right. The right hand side is basically a MOS, where you have a gate metal, you have an oxide and you have a silicon semiconductor which is N type and P type, and then I am giving a gate bias which is 0. So basically I have shorted this gate to silicon. We have already seen that if you want to find out, so you see the first statement which I have written here, the flat band is the condition with the energy band EC and EV of the substrate, this one is flat at silicon dioxide interface, which we have already seen in our previous discussion. If you do not apply any external bias, they will be exactly flat at silicon dioxide. So, with silicon dioxide interface, you will have EC, EV, right, and then EFI. If it is an N type semiconductor, this will be EFS, and they all will be straight, right, primarily meaning that you have not applied an external bias, right. And if you therefore sum all the contact potentials from the gate through the external connection into the bulk, I will get V of F, or the F of VB phi, or this can be written as phi of VB to be phi of gate minus phi of bulk. We have already done this in our previous lectures, and therefore I will not stick to this too much. What does it tell me? It tells me that because of the difference of contact between gate, which is a metal, and the bulk, which is a semiconductor, you require to give an extra push for the electron to move from gate material to bulk material, or vice versa, and that is given by Vf, F of Vb in this case. What will be your flat band in this case? Simply VGB, gate to bulk. VGB will be equals to VFB, which means that since you did not apply any bias, there will the charges or the channel charge per unit area will be 0, and of course since the charge is 0, surface potential is also very much equals to 0, right, and your VGB will be equals to VFB. That is what is a flat band voltage condition which you see. This is the diagram which I was referring to in the previous stage. So, I have a MOS structure, I have a metal here, I have an oxide here, right, I have a semiconductor here, right, and let us look at the MOS structure here. So, we already know that at equilibrium phi m minus phi s is the value, right. So, what we do is if you see, your chi of silicon dioxide is very high, right, it is relatively very high. Similarly, the chi for silicon is 4.05 electron volt, which is written here for silicon we have written here. Therefore, this is the conduction band edge of metal of the silicon, and this is the conduction band edge for on the metal side, right. Now, if you look at the right hand side, then q times phi s, which is the amount of energy required sorry, the amount of energy required for the electron to move from the semiconductor Fermi level to its vacuum level, is given as q times psi I, will be given as this much. This is the electron affinity, this plus this is nothing but Ec minus Ef. So, you see what we have done, we have written q of psi of s is equals to chi silicon plus Ec minus Ef. Higher the value of Ec minus Ef or chi silicon, the value of my surface potential also becomes larger, and that can be visible from this particular graph, or from this particular schematic at least. This is one aspect which I wanted to showcase to you, which means that the surface potential, or q in times psi s, is dependent on two factors, and the first factor is electron affinity, and the second factor is the difference between conduction and the Fermi level, EF, conduction and the Fermi level. Whatever I am teaching you is for, let us suppose this is for a p type material, I would request you to go for and discuss with for n type material as well. Please try to do that, how this is working. Now, this is n plus polysilicon, right. This is n plus polysilicon. You can also have metal available here. This is an oxide layer whose band gap is typically 9 electron volt, very high, but the band gap between in silicon is approximately 1.1 electron volt. This is typically 1.1 or 1.2 electron volt, which you see. The value is 3.1 electron volt from the conduction band edge of the silicon to that of oxide layer, right. And this gives you a brief idea about the flat band condition. So, I have not applied any bias, the bands are absolutely flat, primarily meaning that no charge carriers are developed, and therefore, the potential is exactly equals to 0, right, and that is what you will come to know. Now, let us come to the first part of it, and that is known as the accumulation region. What is accumulation region? Is when you apply gate to bulk or gate to bulk negative potential. When you apply a negative potential, then the majority carrier concentration, right, near the surface, which surface? Silicon dioxide surface, become larger than the equilibrium electron hole. I will give an example. Let us suppose at T equals to 300 Kelvin, and with no bias and let us say it's because of thermally generated charge carriers, you will have some electron hole pairs generated, right. Let us assume those to be as a thermally generated electron and hole pair. Now, when you apply a negative bias, you tend to generate extra charge carriers there. So, therefore, the majority carrier concentration near the silicon dioxide interface becomes much larger than the equilibrium electron and hole concentration. And when you apply, what is the meaning of negative? Negative primarily means that my gate to bulk potential or gate to body potential should be below VFB or VGB, right. So, which means that let us suppose your VFB is equals to minus 1 volt, then if you apply a gate to bulk of minus 3 volt, then we define this to be as an accumulation, right. And this is, so let's look at the fact of what happens if it is negative. Very true. If we apply a negative bias, which is VGS less than 0, then all my holes, if it is a p type semiconductor, all the holes in the p type semiconductor will be rushing towards the silicon dioxide interface, and you will have a large amount of charge carriers, positive charge carriers sitting somewhere here in the interface region, right. And this is accumulation. You are accumulating the charge carriers there, the same type of charge carriers as there. So, if it is a p type material, you will be pulling the holes. If it is an n type material and apply a negative bias, the electrons will be pushed backwards and the holes will be created near the region, right. So, you see for an n type semiconductor, if you want to form the holes as the charge carriers, then you have to give a negative bias to pull the holes, and for a p type semiconductor, if you want to form n type layer of inversion layer, then you have to apply a gate voltage which is positive in nature. So, at a very early instance you can understand the difference between a positive bias and a negative bias. So, you see I can safely write down Vg to be equals to flat band voltage plus surface potential plus Vox, already discussed with you, and Vox, the voltage across the so this is also psi Ox which I am using, is the voltage across the oxide layer is given by Vg minus Vfb, the gate voltage minus flat band. You apply the gate voltage, you spend some of the gate voltage in flattening the band, and the rest of the voltage appears across the oxide layer, and it is given by substrate minus times substrate by Cox. So, you can use it as per unit area also, or you can use it as a total charge also. This is the band diagram in the accumulation region, right, and it should be clear to you before we move forward. I told you earlier that in the accumulation region you are accumulating holes near the semiconductor interface, oxide semiconductor interface. So, this will be an area where you will be accumulating holes. As a result, the energy levels will start to move up, and that is the reason you see these are all moving up, right, moving up. And as you can see, valence band has been closer to the Fermi level, which primarily means the number of holes have actually become larger in this case as compared to anything else. Fine. We define the new value of the Fermi of the electron affinity as q times chi prime, where chi prime is the effective electron mobility when you do have a bias being applied on the metal side, right, and on the p plus poly on the metal side. As you can see, my Fermi level is almost equals to the edge of the conduction valence band here, right, and if I assume it to be as a p plus poly. So, it is a p plus poly oxide and you have a semiconductor which is again a p type, right, you can have the such type of accumulation. More is the bending, upward bending towards the semiconductor, more it goes into accumulation, more will be the charge which is getting accumulated at this stage in the semiconductor, right. So, please keep this in your mind as far as this concept is concerned, right. Let us come to the last stage, and then we will do inversion later on, but let us come to the depletion stage. What is a depletion? Depletion is when you give a VGS value, gate to bulk or gate to source, gate to body value slightly positive, but not very large positive. When you give a slightly positive, I already discussed with you, what will happen in this case is, interestingly, that the oxide, if you apply a positive, let me show it here itself. So, if you apply a positive bias here, then the electric fields will be all in this direction, right, all in this direction, right, and then when the field is in this direction, you will be basically depleting this area of free charge carriers, because all the holes will be shifted. Let us assume that this is a p type semiconductor and Vg is greater than 0, then holes will be dropped below the surface silicon dioxide, and there will be a space charge or depletion region formed between these two. And the width of the space charge, which we had defined earlier as xd, will remain constant as you move from this end to this end. Please understand this point very clearly. Why it will be constant? Because I am not applying any bias on the right hand side of the diagram, on the left hand side of the diagram. I am applying a bias in the top side. So, if I assume that the potential electric fields and potential are exactly the same in all the direction, the amount of potential visible at this point in the interface, so at these points, if you see, the effective potential visible to you will be after the oxide voltage drop, and that potential will be responsible for forming the depletion region, right. That potential will be responsible for forming the depletion region, and it will be constant as you move from left to the right, it will be constant. However, we will see later on when we use MOS as a 3-terminal device, that once you apply a potential on the right hand side or on the left hand side, the depletion thickness will not remain same across the whole device, but it will go on becoming smaller and smaller or larger and larger as you move from one side to another when you apply a bias. Now, as written here, if you apply a small positive gate to source voltage, the minority carrier concentration will leave near the oxide silicon interface, and only fixed or acceptor or donor ions will be remaining there. So, these are fixed charges, and therefore, they will form a positive bias at this particular point. look at this right hand side curve here, this diagram here. In the depletion region, it will, the bands will be moving downwards towards the semiconductor side, but it will be not very down, it will not be too much down, it will be just going a bit down, right. And we define Vg to be equals to Vfb plus psi s plus Vox, already discussed. Psi s has got a formula given by this, and Vox can be given by this, and we can write down this to be as Vg equals to Vfb plus Q times Na W depletion square by 2 epsilon silicon plus Q times Na W depletion by Cox. So, on what factors does the gate voltage or the basically the voltage varies, or on what part does the gate voltage go on. So, this gate voltage which we apply will go on to make the bands flat first of all, then some of it will fall across the oxide layer and the rest of it will appear as a surface potential, which will be actually depleting the channel, right. And this one is relatively easy to handle, because I am again assuming that W depletion is constant. In reality, not true when you apply an external bias either on the drain side or on the source side of a MOS device, right. So, this is the depletion region. Let me come to the very important part, and that is known as the threshold condition. So, we have understood flat band, we have understood accumulation, we have understood depletion. Let me come to now inversion and threshold. Now, if VGS which you have applied, gate to source voltage, is quite high and it is equal to threshold voltage, we define a term threshold, then when my VGS is exactly equals to the threshold voltage, so what will happen when VGS was slightly positive, I was able to push the holes below, and you had a depletion region devoid of any free charge carriers near the silicon dioxide interface. Now, still go on increasing the gate voltage, what a time will come when the electric field will be substantially large to pull the electrons, right. Now, pull the electrons means it will be pulling the electrons from the substrate and source and drain later on towards the interface. Once it pulls the electrons near the interface, you will have free charge carriers available, right. So, you will have these, so you will have free charge region here, you will have free charge region here, and there will be also depletion region here, right. I am not deriving anything here, I am just writing the value of the threshold voltage to be equals to this quantity here. You can have a look from numerical point of view. Therefore, the surface is no longer in depletion, but in the threshold of inversion. How do I define inversion? Inversion, why the name inversion has come? So, you see, if you look very closely, initially this was a p-type semiconductor, right. I had applied a bias, removed the holes from the interface, made it depleted, and then I am doing I am putting electrons there. So, the charge carriers have inverted from p type to n type, and that is the reason it is known as an inversion layer has been formed. The voltage at which this first layer of electron comes and it becomes exactly equals to the number of holes initially, we define that to be as the threshold condition, right. So, if you want to therefore have electrons available in a p-type semiconductor near the silicon dioxide interface, you have to give a gate voltage equal to the threshold voltage of the device. Let us look at the band diagram of a threshold voltage, right. Let us look at the band diagram of a threshold voltage. You are applying a positive gate bias, please understand, which means that you are applying a negative towards the semiconductor. Now, you know that it is minus Q times V, right. So, what will happen is that the bands will be pushed inside or down, it will be pushed down, means in energy domain it will go down when you apply a positive bias at the metal side. So, when you apply a positive bias at the metal side and assuming that the metal to be an n-type poly, my conduction and Fermi level are almost overlapping with respect to each other and my valence band is very far off. And then what I do is I will see that this is EV, EF, EI and EC, the conduction band, intrinsic Fermi level, the Fermi level here and the valence band. Since EF was close to EV, I can safely say this to be as a p-type semiconductor, right. Now, what has happened is, you see, when I applied a bias on the metal side, thereby pushing it downwards, if intrinsic Fermi level goes below my external Fermi, the Fermi level which is there for the metal, which is there, this one EF, then the type of carriers actually get reversed. So, what will happen when, suppose this is my EF, right, you applied a potential EY in flat band was something like this, this was the flat band EI, you applied a potential, bending takes place and bending becomes exactly at the edge, this is the edge of the depletion which you will find out. You still go on increasing it, you will get something like this. So, it goes below EF, which means that if initially it was a P type, now it becomes slightly an N type. And we define Q into phi B as the bulk potential here, right. Q is equals to Q into Q into phi B is the bulk potential, right, and that is what the effective potential is available with you. Let us look at this point D. This is D. Higher the value of D, more the bands will be bent downwards, and therefore more will be the number of free charge carriers, in this case electrons, because it was initially P type, right, and this can only happen when you apply an external positive bias to this case, right. So, this is the threshold condition sort of a band diagram I want to discuss with you. Now, let us come to the definition of strong inversion region, right. Strong inversion will happen when VGS is very large as compared to 0 volts, it is pretty large, right, and becomes large, very large. I will don't look at the formula at this stage, it becomes very large. Let me see, I have a diagram available to me now, I will explain it from here. If I want to make it, so I will change it, I will change my explanation slightly. When this EI becomes just touches EF, so when EI exactly equals to EF, that is the onset of inversion, and when EI becomes further down and this distance, suppose this is X and suppose this is Y, when X equals to Y, right. So, it has now become lower from the Fermi level by that much as it was initially higher than the Fermi level, then we define that to be as a strong inversion, right. So, inversion is when this EI meets with EF at the interface. What is strong inversion? When EI crosses EF and almost it crosses up by how much? 2 times. So, initially suppose it was here, this distance was X and this distance was also X, then we define this to be as a deep inversion. Please see, as you move inside the semiconductor, your variations are not there. If the variations are only visible to you when they are very close to the interface of the semiconductor interface. So, this is the right hand side picture gives you the electrons getting attracted, large number of electrons are available here and you have Vg much larger, and this gives you an inversion layer. Now, look at the left hand side, the explanation of this thing. You have on the left hand side, you have the maximum width of the depletion region is given by 4 times epsilon silicon phi bulk upon QNA, and the inversion layer density which you get is C. So, C into V is Q. So, Q inverse is negative because I have inverted it. So, I get a minus sign here. I multiply Cox Vg minus Vt, where Vt is the threshold voltage. Why? Because if you apply a gate voltage out of which, let us suppose you apply a gate voltage of 2 volts, then out of which 1 volt is just gone to form the channel. So, what you do is that you subtract the threshold voltage from the gate voltage to see the effective gate voltage available to you, that you multiply with Cox to get the total inversion charge. So, this is the inversion charge definition as far as strong inversion region is concerned. We will take up 3 terminal MOS device in the next turn. Thank you very much.